I'm Nicola Cibin, and today's presentation will be about cybersecurity threat, attacks, and mitigation in operational technology systems. I just realized that perhaps it is not a good idea to put an acronym in the title, but we will see just in a minute what with systems and how we can create it from IT and information that is information technology system. So even though the presentation will be focused on the energy sector, most of the concepts and the insights that we can get from this presentation can be generalized to whatever industrial control system and industrial process. So during the presentation, first of all, we will have a brief introduction about the digitalization of the electrical power grid, what kind of opportunity this digitalization provides to operators, but also customers, so all the stakeholders involved in the electrical power grid. But then we will also discuss what kind of cybersecurity challenges the new digitalization brings to the table. Then we will start discussing what kind of cyber attacks can be performed in these applications. So we start by analyzing this architecture, what kind of systems and services are deployed in these applications, and we will briefly describe the IC 150 standard, and we move to the IC standard, which is by some recommendation to secure standard. Then we will discuss some security concerns specific to applications and standards. Finally, during the section, we will present how cyber attacks can directly impact the physical layer of the electrical power grid. Then we will provide some real-life example of cyber attacks that has been successful in the last decades, and we will try to analyze them as in depth as possible as the time needs. Finally, we will discuss some kind of defenses and advanced defenses that can help us mitigate and prevent cyber attacks happening. Then we will conclude our presentation with some conclusions, some reflection, and some research direction, which could be carried on by researcher and also my PhD. So, just a brief introduction about myself. I am Nicola Cibin. I hold a master's degree in Telecommunications Engineering from University of Padua here in Italy. Got it in 2021. After that, I worked for 2 years as a research assistant at Aalborg University in Denmark before starting my PhD in TU Delft, in particular in the cyber resilient power grid group, research group. My research interests span from telecommunication networks, cybersecurity, smart grid, and blockchain. And in the context of InnoCyPES, my focus is on cybersecurity. So even though it's just the end of the week, so we heard many times during the week what digitalization means for the electrical power grid. Let's just briefly remark it. So electrical power grids are transitioning first to paradigm of smart grids, and shift involves 3 factors. First one is decarbonization, which means adoption of renewable energy, like for instance, like systems lines. Moreover, these are no more deployed and controlled in a centralized way, but they are deployed all over the grid in a decentralized way. So we don't have anymore centralized and direct control on these resources at further complexity level, even though what we are mainly interested in this talk is digitalization. Because, okay, digitalization allows to have a lot of services and opportunities like grid services for automated demand response. So, given the amount of data that we have available, we can provide services like predictive maintenance or also a faster and automated fault detection and clearance all over the grid. But still, all of these novel opportunities comes at a cost. Indeed, provide these novel opportunities, these novel services need a further interdependence with measure the operation in our systems. Just to give some definitions, technology, we refer to those systems were mainly used in companies and businesses to take care of the processes and data management. And traditionally, they operate independently from systems. And usually, they include standard personal computers, server, routers, kind of systems. Whereas with operational technology, we refer to systems that are deployed in the field, or they are the main components in industrial control systems. And historically, they are gapped from the public network, meaning that they were not accessible public internet or not even from the IT infrastructure. This was mainly for providing safety and reliability, and access a system only being there physically, the attack surface is better off reduced. But now, given that these IT and systems are a lot of really interconnected, IT services, any cyber attack is able to reach the information technology infrastructure, then has the opportunity to move toward the operation. So that indeed the attack surface is increased, also paves the way to novel threats that we never experienced in the last years, but then in the last years we've experienced quite a lot of them lately. Also, a huge difference between cyber attacks in IT and OT systems is that when a cyber attack is successful, the information technology really affects the data of the users or cause financial losses to companies. I'm not saying that these are not problems, are huge issues, but still, the difference is that when a cyber attack is actually able to be successful in technology, so in industrial control system, in that case, we have an instant impact, which is a physical impact, which lead to fires, explosions, blackouts, lead to real physical harm to people, a real threat that we tackle quite seriously. Also, here we have a design that represents the evolution from conventional substation to the novel concept of station. We can see that in conventional substations, we have hardwired connection between one component and the other, whereas now we have almost always have all the components connected to a single bus or directly to a single switch, meaning that even if one single component like the substation network is optimized, potentially this compromisation move to also other systems in the substation. So now let's move even more into detail. Components we have there and how we can attack those components. So here we have a high-level view of the substation. here we can see that it can be divided in 3 main levels. Top, we have the station level. We have usually the operating station, which is used by operator to control the station status in real time, and control circuit breaker if needed. Then we have the engineering workstation to different devices. The station, we have the human machine interface, which, as for the operating station, is used to monitor our digital substation, but more in a less granular way, providing more high-level insights to the operator. And finally, we have the GPS time server, which is crucial in the station to synchronize the various measurement and the control C. And then in the bay level, we have a number of intelligent electronic devices that are used to implement control and protection algorithms, transportation, overcurrent protection to scan systems. And as Nadine discussed in her presentation yesterday, this level we are seeing moving from a lot of independent physical IDs to a more centralized kind of infrastructure where we have multiple virtualized IDs deployed on a single server. And as Nadine discussed yesterday, this it will provide a lot of benefits in redundancy, reliability, but it also paves the way for cyber attacks. And finally, on the lowest level, we have the process level, when we have the actual interaction with the system, so with bus, voltage, current. So we have current transformers, voltage transformers, and transistors are connected to merging unit. In turns, convert analog signals, which is then sent to IDs to control the status of the substation and of the area. Still remember that this is on high-level topology of a digital substation, and actually, from a real network perspective, the devices are not connected in this way. Usually, we have some kind of topologies, like the one relying on the parallel redundancy protocol or the high availability seamless redundancy protocol that are used to provide redundancy in the network, also seamless recovery in case of faults. So as Nadine introduced yesterday, one of the new standards introduced to manage stations and control all different communication between the device is the IC 6150 standard. The standard posed by IC and meant to provide novel power system automation and protection services. It has a lot of features, but the main one are interoperability, to provide the interoperability between different devices deployed in the station. And we have a number of communication protocols and signals to breakers and to report the measurements to the protection algorithms. And it also defines object-oriented data model, how to perform substation automation, how to be scalable and flexible, and also other things. But what we are mainly interested in during the presentation are the cybersecurity definitions, standards, recommendation, and how protocols defining this standard are actually not that secure. So in the standard, colors right up. More or less we can get a glance on what it was meant to represent. So on the right side, we have the communication stack of the 5 main protocols, which are defined in the IC 6150 standard. The first one is a generic object-oriented system event, used to send signals from IDs to circuit breaker in faults or maintenance or that we need open circuit breaker. Then we have sample values, which is a protocol used by merging units to report measured three-phase voltage and current to IDs. Then we have the manufacturing merging specification, method specification, MMS, which is used to configure IDs. And finally, we have the routed GUS and routed SV protocols, as which have the same scope as the standard GUS and SV. The only difference is that they can be routed to different LAN and ones. For those of you who have a little bit of familiarity with communication stacks, they can already note that in here we have the GUS and SV messages that are directly injected in the Ethernet level back layer. Then we have MMS, root GUS, and root SV, which are directly injected, encapsulated the TCP and UDP packets and data frame, respectively. But what you will notice is that here we don't have any kind of security layer. For TCP, we don't have TLS. UDP, we don't have DTLS. For GUS and SV, we don't provide any kind of encryption or authentication. And this can be quite a huge issue. Indeed, these messages, these packets are sent around the network unauthenticated, so you can't tell who actually sent that packet in the network. They are unencrypted, so all the devices in the network can receive these packets, read them, whatever they want with the information they get. And also, yes, they are broadcasted, so any device in the network can actually sniff them. You may ask why don't we implement authentication, encryption, or some kind of security measures? And the main reason is because of the timing constraint. When IDs send tripping signals to circuit breaker, it can't wait for the circuit breaker to decrypt the message, authenticate the sender, and then act accordingly. Need to be really need to operate on real time. And even though in the IC 62351 standard, at the beginning, encryption and these signatures were kind of recommended. Then they realized that if they are actually implemented in these substations, we wouldn't be able to meet the 3 millisecond timing constraint. So right now, the recommendation is to use hash-based message authentication codes by the message authentication integrity. And this means that when a packet, it is a SV or a GUS packet, are sent into the network, we append at the end of the packet a short message. Is used indeed to authenticate the sender and to provide the integrity of the packet. The issue is that even with this solution, we have some drawbacks. Because first of all, we need infrastructure to manage the key. They're used by the different devices to compute this message authentication code. And so it would require the deployment of key distribution center. And moreover, usually sample value, but also GUS messages are quite small. They are only few hundred bytes long. So adding a message authentication code is usually from 10 to 30 bytes. Adds a quite huge overhead in our communication system. And this is everything but ideal. So more in detail, we have quite plenty of vulnerabilities and weaknesses in these protocols, which can be exploited by cyber attackers to perform the attacks in the system. So for instance, for the MMS protocol, we have vulnerabilities ranging from the unauthorized command injection, which allows attackers to attack the command network. Also, there is the of information disclosure and IO service. But what we are more interested in this presentation, also because that the attacks have been actually performed, real-life cyber attacks, are the GUS and SV vulnerabilities. As we mentioned before, these GUS and SV messages are broadcasted, are not encrypted, are not authenticated. So once that an attacker is able to intercept these messages and inject those messages by slightly changing the content of the message and cause a circuit breaker to open, so there is no fault, or they can start reporting false measurements to the IDs. And this can be seen from two different perspectives. First one is when there is no fault, but the attacker and sample values messages around the network saying that actually there is a short circuit at some point in this substation. And this will cause the detection algorithms to react or to open the circuit breakers, even though there was no reason to open it, no real fault. The other option is send sample values frames reporting normal conditions, even though a fault was happening. And even though this might sound strange, we will see that this is what actually happened during the quite famous Stuxnet attack that we'll describe later. Here we can see two Wireshark acquisition. So here we acquired the network traffic in this substation. And on the left side, we can see the original GUS message, which was sent from General Electric IDs, a Siemens one, not sure, but one of those. And in the left side, we can see the injected GUS message. We don't have the time and not even the site to analyze all the different fields that are in the packet, but if we compare the two packets, they're exactly the same. So if a circuit breaker receives either of the two GUS messages, for it, it will be impossible to tell them apart, because both of them but here we can see that in the original message, here we have this Boolean false, which tells the circuit breaker whether it has to open or stay closed. As long as that value is false, the circuit breaker will stay closed. But as soon as we inject our GUS message, that value changes true, the circuit breaker will open. On the other side, here we have also an acquisition of sample values frame, which report phase, current, voltage. And here we can see normal operations, here on the right side, normal operations in which the actual values for current and voltage are reported. Whereas on this side, we can see that we just injected our sample values, stating that all these values were 0. So some kind of fault is happening. So, so far, we've seen that this kind of cyber attacks can potentially be performed. And we saw that we can use these cyber attacks to report false measurements or to open circuit breakers maliciously. But now we want also to focus on the actual physical impact of such successful cyber attack. So as we can say, cyber attacks can lead to circuit breaker opening. So it could lead to abnormal operation or lack of control in our electrical power grid. And by in turn, this could cause an unwanted circuit breaker opening, delayed or blocked fault clearance. And all of these could lead to also power swing situations, frequency swing situations, which in turn lead to cascading failures. Once that one circuit breaker is open, other lines could be overwhelmed, overloaded. one will cause also other circuit breakers to open around the grid, and one step after the other, the whole grid could collapse and lead to generalized blackout in our grid. Indeed, it has been shown that cyber attacks can induce a significant speed up in the cascading failure mechanism compared to real faults. And it has been shown that this increase is in the range of the cascading failure in the case of cyber attack is 3 times faster in the case of actual fault. So here we have also a really great study in led by Ioannis Parentis. He analyzed how different types of cyber attacks can affect the stability of the electrical grid under different perspective. So he analyzed how manipulation of measure points, how the injection of different malicious command, and how the inducted communication delays can affect either the resonance stability, the converter driven stability, the rotor angle stability, and the voltage stability and the frequency stability of our power system. So for those of you that are interested in this cyber attacks implication on the physical layer, I really strongly suggest to take a look at this paper because I found it really interesting. Okay, before moving to the modeling of cyber attacks, do we have any questions there from the attendance? Okay, so later in the presentation, we will analyze different real-life cyber attacks happened in the last decade. But in order to analyze them and understand hackers' behavior, we need a framework and the different steps hacker to compromise our system. So one of the most popular and used framework to model cyber attacks is the so-called cyber kill chain. This framework has been developed by Lockheed Martin, and it is a framework meant to help analysts and cybersecurity specialists in identification and prevention of substation, but mainly in the understanding of how the attackers operated, how they were able to network, and what kind of actions are performed in their system. So here we can see the 7 steps. First one, the finance. So during this phase, the attackers try to gain as many information as possible about their target. So can include what kind of systems are deployed in target infrastructure, what kind of services are running, what are the version of both hardware and software component, but also information about the employees. So while addresses, the format of the templates of the Microsoft documents, for instance, which can be really helpful during phishing attack, and all of this kind of information that, as we will see during the presentation of the different attacks, they are fundamental for cyber attackers to actually perform a successful cyber attack. Then the next step is the so-called weaponization, which the attacker prepare the malware to be sent to a target. So they prepare a specific malware which can fit exactly all the information they gathered during the reconnaissance phase. And then this weaponized malware is delivered to their target delivery phase. The delivery can span a lot of different methods. The quite and common phishing email to creation of public websites, or also the physical delivery of an USB stick and connected by the employees, business systems, or even directly structure as following. Then after that, our malware has been successfully delivered to a target. You have the exploitation and installation phase. So the first phase, the exploitation, malware exploits vulnerabilities in the system. Then by exploiting these vulnerabilities, the malware is actually able to install itself in the system and then also propagate to other systems around the network. Then once that the malware is in the network, you have the phase in which the malware is able to locate the attacker infrastructure, and so it's able to use tunnel to perform malware updates, change his behavior, or actually start the physical attack. At the end, happens during the action of objectives phase. Last phase, we have the actual cyber attack happening. We have the actual opening of circuit breakers. We have the deletion of data or the encryption if it is a ransomware attack. So in the last phase, we have the actual act on. The cyber kill chain is a great framework, but it has its own limitation because we have only 7 steps, which are not that great to model more complex attacks. So a slightly more complex framework is the so-called MITRE attack framework, developed by Passion. Scope is similar to the cyber kill chain, but as you can see, it has many more steps, which allows for a much more comprehensive and granular modeling of the cyber attack. Still, this increased modeling complexity might be an overkill in some cases because most times we don't have that many information about cyber attacks. So using it as a framework can be quite difficult. Indeed, during the remaining of our presentation, we will use the cyber kill chain model, all the different cyber attacks that analyze. So before going to lunch, let's have just a brief introduction about the real-life cyber attacks that discuss in the afternoon. So here we have high-level representations of the major cyber attacks targeted the energy sector in the last 14 years, so starting from the quite popular Stuxnet, run their facilities, the Black Energy Free, Industroyer, and Industroyer 2, and another attack which all happened against the Ukraine energy sector, marked red in the figure. Then we had quite a long espionage campaign on the Dragonfly 2.0, and the tomato fusion attacks, which was a quite long espionage campaign, which was carried on in Europe and North America from 2011 to 2019. And even though in this campaign the attackers were mainly interested in gathering information and be used to actually perform the attack, during this operation, given that they were still operating in operational technology systems, it was possible that during the reconnaissance phase, some steps could have also led to the unwanted opening of circuit breakers or unwanted service of this. In this case, we were being quite lucky that they were able to perform the exponential phase without actually affecting the stability of the As you can see, from 2024 onwards, question marks, because okay, right now we're not aware of any attack happening in 2024, but the question is not whether a new attack will happen, but when will it happen. So we have to be prepared and deploy all different standard and advanced defenses that we discuss at the end of. Moreover, these kind of events are low frequency, luckily, but also high impact events. So for this reason, it's difficult always be prepared. Because if you had a huge number of cyber attacks, you can train on them, you can understand how attackers operate, so you can defenses. The fact is that we don't have such information. We don't know when they will attack. We don't know what kind of technologies, what kind of vulnerabilities they will exploit, or what kind of malwares they will deploy. We are training for something that we don't know. That is the real challenge in here. Okay, so actually before moving to the actual discussion of the different cyber attacks, we'll take some questions. And if there are none, I will just sit for the session. Good afternoon. I see a question from back.
So I have seen some report about the cyber attacks, energy sector were collected by cybersecurity division in Denmark. Have collected the events past about the real life cyber attacks. It turns that the majority of cyber attacks from IT, but and also it's only one or two cases that eventually affected. So here I want to here I'm interested to or curious about how so should we this research in cybersecurity more focus on IT or OT, or how do we design the solution for cybersecurity? Whether we should look from IT perspective or at beginning or OT.
Yes, thank you very much for the question. Indeed, as you mentioned, most of the time the cyber threat is coming from the IT. That's true, because the IT most of the time is directly connected to the internet. Also, many people have access to the infrastructure, so it is way easier for attackers to compromise the IT instead of the IT or instead of the OT infrastructure. Indeed, we see it in later in the presentation, also in other surveys that SANS performed in the last years. So yeah, that's true. The fact is that now, as I mentioned at the beginning, IT and OT are much more connected, much more interconnected. In that, okay, the attackers, first of all, compromise the IT, but then for them it's fairly easy to move to OT environment if the appropriate cybersecurity defenses are not implemented, or if the different systems like switches, firewall, routers are not properly configured. So yes, if we are able to keep the cyber attackers away from the IT, we already solved an issue. But most of the time, we should just assume that the IT has already been compromised. So let's assume IT has been lost. So now let's try to save the OT, which have the physical impact on our electrical power grid. That's the main assumption which is leading all the research in the OT infrastructure. That IT has lost, what do we do now? Actually, Guanja had another question. I mean, if you want to finish the discussion with Guanja, then we can move to the next ones.
And maybe as you mentioned that if we assume IT is lost, because the critical infrastructure here for power system is SCADA. So if we don't have a SCADA, I guess system cannot run.
Yes, but usually SCADA is already considered OT. So the SCADA system is already part of the operation technology infrastructure. So when we talk about protecting OT infrastructure, we are already talking about protecting SCADA. Because indeed, as you said, if SCADA is compromised, we already lost. Yeah.
So out of curiosity, we have so many different protocols and techniques to secure a system independently of the specific scope of this. So my question is, what prevents using well-known and established result? With reference to one of the slides that you showed us previously, for instance, it's quite easy to solve the goose vulnerabilities. You can use a secure authenticated side channel on which you send an ID of a message and its hash-based signature. You can also encrypt everything before sending. So you are not, you send the encrypted data, you're not encrypting while transmitting. You encrypt before and send respecting what the standard says. And then you have the side channel, which is authenticated, secure, and allows you to send the hash. So you can compare, once you decrypt, you also compare with the hash, and you are secure. This is easy enough to be implemented with standard technologies and libraries. And also with regard to the injection attacks, what prevents the use of a simple parser, which simply allow passing authorizer commands, immediately discarding everything else. No attacks can pass through. So we already have the technologies. Why is not possible to use them? Thank you.
Yes, thank you for the question. You're right. We have all the technology needed to secure such communications. Indeed, from a standard cybersecurity computer science perspective, those kind of attacks are kind of trivial. We are used to much more complex and elaborated attacks. The issue is that in operational technology infrastructure and even more in digital substations, we have to rely on legacy systems, which are decades old. So we also are a rollover of new equipment, which is not as fast as in IT. In IT, we can change the equipment every 5 years. There is no problem. Instead, in the OT environment, we can do that because that will mean the stop of operations. Also, the cost of the OT equipment usually is higher, so it's not that easy to update those systems. Then adding to scheduling of systems, like we discussed before, for instance, a key distribution center or to use a side channel, increases the complexity of the network. And usually, network architects which operate, which work in the OT infrastructure, they try to keep it as simple as possible, because the least components, systems, services you have in the OT environment, the less likely is that something fails. So just keep it as simple as possible. The third point, you mentioned about indeed using encryption or authentication to prevent injection of messages or this kind of attacks. The issue is that in operational technology, again, specifically in digital substations, we need these measurements to be sent, to be received, and then processed by the protection algorithms in less than 3 milliseconds from when the measurement has been done. So given that we need to have a latency lower than 3 milliseconds, and then we are publishing one new sample value every 100 microseconds. So we need, in less than 100 microseconds, we need to either encrypt the message or to add a message authentication code. And unfortunately, if we use RSA or AES, so either asymmetric or symmetric encryption, cryptography, these timing constraints cannot be met. That's the main issue that we are having in OT environments.
There are simple ciphers which meet these real-time requirements. They are already available. They are not asymmetric, they are symmetric key-based.
Yes, for instance, the standard suggests to use HMAC, which is a symmetric key, not encryption, but authentication system. So it is recommended. The industry is testing it, but there are issues because indeed legacy systems are not that easy to be updated to support message authentication codes. And also you need the infrastructure to handle the symmetric key, unless you just add the symmetric key at the manufacturing level. So when you produce the device, you already had your symmetric key, and once it is deployed, it is already working. But otherwise, you need a plan to manage all of these keys or an automated infrastructure.
Okay, thank you very much. So the key problem is just that we need to substitute all the infrastructure with new generation.
Summarizing, yes. If we summarize all our discussion, we can say that, yeah.
So in the future, this will not be a problem anymore. Okay.
Potentially, yes, but given that those systems are acting on a really critical environment, we can't just put a Raspberry Pi or a general purpose device in there to perform these kind of services, but we need a hardware component which has been tested for potential years, so every eventuality has been already evaluated. We know that it will work real time for the next 50 years, because in these cases we can just open a circuit breaker and change the intelligent running device. We can just do that. We can't afford any downtime in this kind of infrastructure. That's the main issue. Yes. Thank you very much.
I have time to ask.
Yeah,
great. So I have two questions. One of them is a bit high level. The other one is maybe just a little bit low, but you know, like it's. But the low one, can we go to the slide before? I guess yes, this one. Yeah. So there is this, for example, goose messages, but also the route goose messages. So I assume the regular goose messages are mostly for operation, and you know, like they should be really fast, right? Real time, right? Or they go to IED, yeah, or but the routed ones are for inspection, looking at what's happening, or
so routed goose have the same objective as a standard goose. So both of them are used to send 3-pin signals. The main difference, indeed, as it is written in the slide, is where these messages can be sent. So in the case of goose messages, can only be sent inside the local area network. Instead, with routed goose can be sent also to other local networks. And the main use case is for inter-substation communication. So to send goose messages from a substation to the other. With goose messages, we can't do that because they lack the IP layer, so they can't be forwarded from one network to the other. Whereas with routed goose, we can do this.
Yeah.
But yeah, then we have the issue of the timing constraint.
Yeah.
But we just do the best we can do. I mean,
yeah. So like
you can't go faster than light.
Yeah. Yeah. Right. So like our good, that's probably slower. Huh?
Yeah, the timing requirements are slower because it is infeasible to respect those kind of delays.
So like, but these attacks are towards then regular goose and like the.
Well, potentially those kind of attacks can be performed also against rooted goods, because also in that case, we don't perform any kind of encryption or authentication. So they're just sent in clear text, so anybody can sniff these packets, so they can acquire the packets, just check what's the structure of the packet, and modify and reinject them.
Okay.
Also, in the case of if rooted goods are actually implemented in digital substations, it can be even more dangerous than with standard goods. Because with standard goods, the attack can be performed only when you are inside the local area network.
Yeah.
Whereas with rooted goods, the attack can arrive more or less from everywhere.
Yeah, right.
Then depending on the switcher configuration, switch configuration, but potentially they can arrive from wherever in the network.
Okay, thank you. The high-level question is about, this is system, like energy systems are pretty, the impact can be pretty drastic, right? With the OTs and everything. I don't know other domains with OT, maybe manufacturing, but if you attack them, probably the consequences are not as severe as like the energy, I assume. So I mean, I just wanted to ask, like, is there such a? It seems like it's such a unique case for cybersecurity, and if there, I wonder if there are other examples of this kind of in this severity level, with this kind of IT OT chain, and like can we get others? For example, in the private part, the healthcare suffers from similar problems, right? So I can say, okay, like the can do etc. But is there another kind of cyber security issues with other systems?
Yes, because indeed OT systems refer also in the infrastructure used in every industrial process. So in every industrial process, usually you have PLCs, which are used to control the industrial process itself. So the speed of the motors, the different machines, how they're supposed to operate. And in the old days, I would say, but it is 10 years ago, 20 years ago, so not that far away from now, those PLCs were not connected to the internet. So they were deployed in the industry, in the plant, but they were not connected to the internet. So the only way to actually attack this PLC was by physically go there and try to tamper them in some way. Now, all of these kind of industrial processes are being optimized with AI, big data, quantum computing, etc., etc. But in order to optimize these processes and perform this kind of analysis, you need a lot of data. And to get this kind of data, you need to connect IT and OT. As soon as you do this connection, as you get the data, the attackers can get in. It's the bidirectional flow in a way. You send out the data, but there is the risk that you let the attackers come in.
So like, what do they do? Like, I mean, I'm just asking, are these methods that you're gonna show or you're gonna implement, like, are they special to the energy domain, or can you use in any sector uses OT?
No, they are quite general purpose.
Okay.
Then there are ways for them to be used specifically in the energy domain, but from a high level perspective, they are general purpose solutions which can be applied to any kind of network, either IT or OT.
Okay, thank you.
Thank you. We have another question from Guangsha.
I just see there's some complexity on the cybersecurity also from cross service, this kind of aspect. So I see not the organization. Yeah, so kind of not only one organization. So I don't know whether you also consider this for research.
Well, thank you for the question. No, not really. I'm not working on inter-DSOs communications. That's not really the focus of my research. But yeah, for sure, the interconnection of systems operated by different DSOs will pave the way to different kind of cyber attacks because you are exposing your infrastructure to a third entity that you don't really know how much you can trust. So perhaps your infrastructure can be the most secure in the world, but then you connect it to another DSO who has the worst security in the world. So also in that case, you have to take into consideration, I mean, just to assume that the other party is not that as trustful as you would imagine. Indeed, there are this concept of zero trust architecture, in which you just assume that none of the systems you interact with are reliable and they are trustable, etc. So just assume that everything is compromised. What do you do? Just to come back to Massimo's question, because I just thing came to my mind. One of the security solutions that right now is being discussed and they're trying to implement to secure GOOS messages and SP messages is to use MACsec. So a VPN at MAC layer. This is kind of the state of the art that industry is trying to test and to check whether it can be a solution.
Thank you very much all for your active participation, and thank you, Nicola, for a very good presentation.